So power functions. So I brought up my power functions here, and I just want to show you some interesting things about it. Now, a power function is like this. It's y equals ax to the b power, and a is that constant, and I want to show you what a does. Right now, a is set at 1. So I want to start by showing you what a does. Actually, here, I'm going to make b equal to 1 also. So there they both are 1. So right now, I just have y equals x, right? So what if b is 2? Then I just have y equals x squared, and I know what that does. But what does the a do on the front? So do you remember what that does? Well, as we get higher, as a gets higher, notice we get thinner and thinner and thinner and thinner. And as a goes low, below 1, look what happens. So that's a fraction, that's 1/10. But look what happens when I go negative. It reflects down there, and then it just gets super thin again. So we'll just leave it somewhere interesting. There we go. That looks fun. So this is the squared. And what happens when we get to an odd one? It goes that direction. Because, of course, then we can take negative numbers, right? And then kind of bounces back and forth. Sometimes is only half of it because it's not defined. Just kind of keeps going to the top and the bottom. And you can see when I have various powers. So look at that. That's to the 10th power. What happens if I go the other direction? What happens if I go negative powers? What happens then? Look at that. That's to the 0.5. So that's the square root of x. That's 0. That's nothing. And now look what happens when I'm down here. Kind of the same thing, only now I have asymptotes. So this is to the negative 5th power. So what happened at negative 1? Let's look at negative 1 real quick. We can sit here and look at that. There we go. So isn't that just, well, we have the 0.2. 0.2 times x to the negative 1. Well, that is just the same thing as 0.2 over x. So these power functions can be a lot of different things. So let's go back to our, oops, I can escape out of that. So let's go back to the power function form, and it's any of this. A and B are just real numbers, but we can have any of those things happen. So let's talk about some special power functions called the root functions. So these are when we have y equals ax to the 1 over n. Well, isn't that the same thing as just the nth root of x? Where we have n is an integer greater than or equal to 2. So here's 1/2 x. We've already talked about that a little bit. Here's the cube root, because of course we can take the cube root of negative numbers. And so they just kind of follow these patterns. And these are exactly what they look like. And that's pretty much what this section's about, is what do these things look like? So let's talk about functions that are concave up and concave down. Now, this is extremely important when you get to calculus. So concave up, that's usually what I call a happy graph, right? Okay, and a sad graph. When we start talking about things like things with cubes and fourths and things like that, we're going to get some functions that sometimes are sad and sometimes are happy. So we get both. And so that's what concave up and down means. In the simplest terms, concave up can hold water. It's like the umbrella. Well, it's like an upside down umbrella because it can hold water. And concave down doesn't hold water, so it's like you normally put your umbrella so that the rain will go up here, right? We don't want it to hold water. So let's talk about direct variation of the nth power. So when we're talking about that, it's very similar to our power function. So you can see this looks like our power function. And we have, this is just called direct variation. So this means that x and y have the relationship of changing this way. So y varies directly as the nth power, and n is greater than 0. So we're not considering, and that would be inverse variation otherwise. So we're not considering when n is negative, because that would put the x in the denominator and make actually inverse variation. So generally speaking, when one increases, the other increases. And when the other one decreases, the other decreases also. So they vary directly, and that's what that means. X increases, y increases, x decreases, y decreases. As long as k is positive, of course. K is negative, then that changes if k is positive. But we consider this a direct variation when it does this. So let's say that y varies directly as the square root of x. And that y equals 16 when x is 4. Find x when y is 24. So the first thing we need to do is find our constant of variation. So we know that y is x times the square, or k times the square root of x. We just have to figure out what k is. And we know that when y is 16, when x is 4, so k root 4, so 16 equals 2k, so k must be 8. Therefore, when we have the equation y equals 8 root x, and so what is x when y is 24? Well, 24 equals 8 times the square root of x. Well, 24 over 8 equals x. So 3 equals the square root of x. Square both sides. X equals 9. And that was the question being asked. So let's talk about inverse variation. Okay? So if something's inversely proportional, that means it's something like k over x, or k over x to the nth power. That's when our exponent is now negative. So as x increases, y increases. This is for k greater than 0, for a positive k. X decreases, y decreases. But the inverse variation does some really odd things, because you saw when we have -1, now we have a formula that looks more like this. So if we just have, but we can see that as one increases, one decreases. And of course, we could see the opposite. If we were down here, we would see the opposite, which is when k would be negative. It would reflect on the axis. So let's take a look at this problem and see if we can figure out. Y varies inversely, so k over x to the 4th power. And we know that y equals 5 when x is -1. So we have a y, we have an x, let's get our k. 5 equals k over -1 to the 4th power. let's see here. We have 5 equals k over 1. So k must be 5. So we have y equals 5 over x to the 4th, or we can write it as 5x to the negative 4th. So when we plug in 0.5, we have y equals 5 over 0.5 to the 4th power. So that's 5 over, let's see, 0.5 to the 4th power is 1/2 to the 4th power, which is 1/16, which is now 5 times 16. 5 times 16 is 80. And that's it to that problem. In fact, that is it to all of this. So we'll do some more examples in class and have a little fun.